Awesome. Right. Cool. So quick starter. Hopefully like a minute and a half. So I had you do a simulation on states of matter last class, and I want you to just quickly, maybe in your notebook or think about it out loud. Number one, describe the movement of particles in a solid. Right, we looked at solid, liquid, gas. We saw a simulation of how particles are moving. I want you to describe how they move in a solid. Number two, I want you to describe what happens to the movement of particles when ice melts to liquid water. So this is a comparison. What happens to the movement when it goes from ice, which is a solid, to liquid water, which is, of course, liquid. And then in number three, I want you to complete the following statement. As the temperature decreases, the movement of particles blank. Right? So please take maybe a minute and a half to either copy and write these answers down or at least think about them, okay? I know we're a small crowd today. We have like 1, 2, 3, 4, 5. So I do want you to participate when I ask. It's about 40 more seconds. What's happening in a solid? What happens when ice melts? And then as the temperature decreases, what happens to the movement of particles? All right, let's start. If I ask the question, you can either shout it out in Discord, use the voice, unmute the mic, or you can just type things in our chemistry discussion. So number one, can someone tell me what happens or what's going on in the movement of particles in a solid? Yeah, don't worry, Benji.
Particles in a solid vibrate in fixed positions. They never swap positions with each other. They're connected in a specific way, but they vibrate together.
Awesome. In solids, it's not that they're moving really slow. Actually, they're moving in place really fast. So what does that mean? They're vibrating or shaking in place, and that should make sense to you. It should be almost common sense when you compare something to a liquid. Then they're moving much more than in a gas. They move very sporadically, and that's why they are gases and not a liquid and not a solid. So yes, movement in particles in a solid, they're vibrating really quickly in place. Number two, can someone tell me what happens to the movement of particles when ice melts to liquid water? So it's kind of a three-part thing. You need to know how they move in solid ice. You need to know how they move in liquid water. And you're kind of comparing what's going on between the two. I think Noe has this one. I know you guys don't see it, but it says Noe's typing. So we're waiting on you, Noe, because I think you're the one writing it. Or if anyone else wants to speak. So Noe says the particles are vibrating in the solid. Good. So that's why I wanted to start with number 1. And then when they melt into a liquid, they move freely, but slowly. Yeah, so I just wanted you to make a complete sentence comparing the two. Particles are vibrating in the solid. So again, here. And then when they melt into a liquid, they move freely, but slowly. Okay. So essentially, they start moving more freely. And then number 3, complete the following statement. As the temperature decreases, so that's kind of the opposite of number 2, going from liquid to ice. What happens to the movement of particles? This is one word answer. Does anyone know?
As the temperature decreases, the movement of particles decreases as well.
Awesome, right. So you can just imagine yourself as like a huge version of atoms, right? If it's really, really like hot, I mentioned this last class to my when I used to do outreach for 5th graders. It's like, what if I put a flame under your feet? And they're like, oh, I would just start running everywhere. And that's pretty much the same thing. I put energy into you, you're going to start moving a lot. The opposite is true. Think about like a really rainy day. I think it rained in my place like 2 days ago. And all I wanted to do was not move at all. I just wanted to stay in place. So as the temperature decreases, the movement of particles also decreases. Cool. And then our question of the day, you can write this in our Discord discussion. Just name an unusual but tasty combination of food, just to start us off. So some examples of this is, this is my opinion, but pineapple on pizza is a very weird combination, and I actually do not like this combination. As I went back to high school, a lot of people put hot Cheetos and then you drip that cheese all over it. I think that's kind of weird, but I can see that working. Or maybe French fries and ice cream. So feel free to share it out loud here or put something in our discussion. Hot Cheetos and peanut butter? Maybe I'll try that. But let's be real, I think it's the hot Cheetos that everyone just likes, and it's so good that it's probably good with anything. My goodness. Okay. Coffee, ice cream, and barbecue chips. So you'll notice a lot of this is like sweet and like savory things. That's pretty cool. And then maybe another 15 seconds. Hot Cheetos and lime. Yeah, but they already make that, right, Vanessa? The lime flavored Cheetos. True. Popcorn and M&Ms. Good. Yeah, nice. Oh, with an actual lime. Okay. Fried chicken and waffles with syrup. Yeah, I heard a lot about the hype, but I didn't like that either. I think there are a couple people typing, and then we'll wait. Mashed potatoes with honey and gravy. So the addition of honey. Ooh, okay. Chicken and mayonnaise. All right. Cool. All right. Nice. All right, let's move forward. So the second part of this unit is intermolecular forces. So I wanted us to go into states of matter because one of the questions at the very end of the simulation was how are these atoms kind of attracted to each other? And this is what that is, transitioning into intermolecular forces. And our essential question for this section is what holds our matter together? Okay. We've actually learned about some forces of attraction, so I want to review that. So what we've learned and what we have already learned about are intramolecular forces. That word intra means within. So we're going to talk about forces of attractions within or in a molecule, and we've already learned two of them. We've learned one in ionic bonding. So NaCl is a molecule, and what are the forces or intramolecular forces of attractions in that NaCl molecule keeping them together? We call it ionic bonding. So we talked about this when we were learning about nomenclature. Ionic bonding is all about magnets of the particular atom/ion. So Na is positive, Cl is negative, and that magnetic attraction is our ionic bond. We also learned about covalent bonding when electrons are shared in a bonds. So this is again another type of attraction. And then we started learning about how to draw these covalent structures by drawing Lewis structures, and then moving on into 3D structures. So we've already learned about these two things. I just didn't give it a name called intramolecular forces. So where are we heading today? We're going to learn about intermolecular forces. So the two letters make a big difference, intra versus intermolecular forces, and these are forces of attractions between a molecule. So they're not in a molecule, so this implies that we have many molecules and we want to know how they are attracted to each other. And again, just to show the comparison versus intramolecular forces, the ones in a molecule versus the ones kind of between and outside a molecule. Okay. So I always like metaphors. So here's a visual metaphor. Hydrogen and chlorine are atoms that form a hydrogen chloride molecule. So here in this visual, it's kind of like we're knitting things together. So if I have a hydrogen atom, or I guess in this visual a cloth, and I want it to kind of be attracted to chlorine, if these are cloths, I need to piece these molecules together with a thread and needle. So this is what happens. You'll notice we have 3 pairs of hydrogen and chlorine stitched together. And then if I wanted to connect all of those together, I could add strips of Velcro between all of them, and now I can have kind of all of them kind of connected, but they're still kind of their own individual self. So if you've ever, held something with Velcro versus like a real stitch with thread and needle, which is the easiest to pull, or which one is easier to pull? If someone can just mention real quick. Which should be easier to pull, the Velcro or the thread? Yeah, the Velcro. Okay, so here's my visual metaphor. The intramolecular attractions are the thread. So notice how those are the attraction in a molecule. And we're going to focus today on intermolecular attractions, how molecules of kind of the same type are attracted to each other between multiple sets. So here the Velcro represents the intermolecular attraction. And as Benjamin and Noe mentioned, the chemical bonding forces are much stronger in the intramolecular ones, the ones in a molecule, versus the ones that are between the intermolecular forces. The stitch, the thread and needle, is stronger than the Velcro. And today we're going to focus on the weaker ones today. So there are 3 types of intermolecular forces. They have weird names, but just bear with us. I just want you to know the terms and have a good big picture about this. The first one is called dipole-dipole forces. Number 2 is called hydrogen bonding. And then number 3, you may have remembered this phrase in the simulation. We also have something called van der Waal, or sometimes we call this London dispersion forces. If you're wondering why it sounds weird, well, You're making fun of their names. So the person's name is van der Waal, and actually another scientist, their last name was London. So two separate scientists kind of came and researched this type of intermolecular forces independently, but they gave credit to both people. So dipole force. I know the word dipole sounds weird, but you should recognize the word that you do know, which is a pole, and I'm sure you know what a pole is, and we'll talk about that. So a dipole force occurs between polar molecules such as H2O or HCl. And a dipole occurs when there is a positive and negative side of a molecule due to electrons. So again, we're going to think about molecules as magnets. So on the bottom left here, I have a molecule of water. Oxygen is an atom that has a negative side to it. And then the hydrogens on the bottom are positive sides of the molecule. It's kind of, imagine that molecule just being a regular magnet where one side is negative and one side is positive. If you're not sure why something is positive and negative, this all comes from Lewis structures, and I had you actually talk about this in the ozone article, if you or not the ozone article, but the I think it was the receptor article, but where does the negative and positive come from? So let's do an example. H2O, we'll do a Lewis structure. So valence electrons, this is 1, and there's 2 of them. Oxygen is in group 16, so it has 6, so 8 total. So oxygen is in the middle, and then the H's are there. So you'll notice I use 2 electrons here and 2 here. So I have 4 remaining. This hydrogen has 2 electrons, it's good. This one has 2. This oxygen has 4, so we need to draw 4 more electrons on here. So now this has 8. So we learned that electrons are negative, so this is where the negative side comes from, and just by default these hydrogens kind of are lacking the negatives as much as the oxygen, so it looks like this side is positive. So this water molecule actually just looks like a magnet where this is negative and this is positive. It's no different than if you had like a battery that has a positive and a negative side. So it's kind of interesting how molecules end up looking like magnets. So moving forward again. So Mr. Dave, I still don't know what you mean. You need to think about molecules as magnets. The positive end of one molecule is attracted to the negative end of another molecule. So here are 3 sets of HCl molecules. And I'll show you again this on paint with the Lewis structures. But the hydrogen is positive, the chlorine atom is negative, and when you set those all together and near each other, all of the negative sides will be attracted to the positive sides, and this will keep going and going. So you'll notice where the dotted line is, showing that this is the dipole attraction. This is what keeps molecules of the same type kind of attracted to each other. It's hard to imagine, but if they were not attracted to each other, you would never be able to see liquids at all. It's because they are close together that we are able to see that these are liquids. And in the simulation, you saw that if they're very far apart, they're gases, and then you start seeing them kind of just fly away, with the example with the glass, right? So let's see this again. HCl. You could do this again, but I just want to show you the work here. HCl. If I was to draw the Lewis structures, there's electrons here. Remember, electrons are negative, so this looks like this is negative, and this side looks positive. So if I have a bunch of these molecules are lying around, they will be attracted in this way. Again, this is negative, so it will be attracted to another HCl part, or the H part of the positives, and it'll keep doing that. So this is kind of just in one direction. I can make this start looking at this in two directions. Notice how this positive H is attracted to the negative Cl. Cl is attracted to that, and then I could actually make like a cube and start drawing this in three directions. But the idea is that the negatives are always attracted to the positives, and this is called a dipole force of attraction.
So why don't they just link up forever? Like, why isn't there just like?
Why are they individual in the first place?
No. Why do like HCl molecules don't? Why don't they just link up with other HCl molecules?
They do
until they're all out of HCl molecules.
They do. This is exactly what we're talking about. They will
So,
continue
like,
doing this.
There's like a 30 HCl molecule? Things like that exist?
I mean, everything is finite. It's not that everything is like infinite, right? So if there's, I know it's weird to think about this, but let's say in a certain amount of space, 30 HCl molecules are hanging out in one spot. They will all kind of create this kind of weird structure where their positives are attracted to its negatives until there's no more than 30. Let's say there's 50, they'll do the same thing, or 100, or 1,000,000, or 6.022 times 10 to the 23. It'll do the same thing until there's no more. Does that kind of elaborate your comment?
Yeah.
Okay, cool. All right, boom. The next type of force is called a hydrogen bonding. Hydrogen bonding is actually just a dipole-dipole. So this is nice. You really only need to know two, because this one is a special type of dipole-dipole. And as you can imagine from its name, it needs to have hydrogen. So it occurs between hydrogen and either one of these three atoms: oxygen, nitrogen, or fluorine. So water is the perfect type of hydrogen bonding because water has both of these atoms, hydrogen and oxygen. I want you to look very carefully at this picture because the hydrogen bonding we are talking about is not the one between the O and H of the same atom of the same molecule, but rather the ones between molecules. So you'll see on the bottom left, the O and H is attached through a covalent bond. So those are intra, meaning in a molecule, and we're focusing on the ones between the same molecules, but between them. I don't know if that makes sense. So the oxygen is attracted to a hydrogen of another molecule. That is hydrogen bonding. So notice how it's very similar to the HCl, the one that we just did. Okay. And then let's just see a even bigger picture. So here, oxygen atoms in water are negative. So I think this is in red or orange. So all the negative oxygen atoms are attracted to all the positive hydrogen atoms in different molecules. So everything that is dashed in this image is a hydrogen bond. So notice how that attraction is between the molecules and not in the molecule itself. So this will make much more sense when we talk about the applications in just a few minutes, because you've actually have witnessed a lot of hydrogen bonding in your life, and Yeah, but let's hold on. I want to show you hydrogen bonding in biology. So hopefully you learned a little bit about this last year. Hydrogen bonding is very important in biology. And the part where it's really important is in DNA. All living things contain DNA. This is where you get your genetics from that you pass on. So that's why you look like a lot of your parents and everyone else in your family. And what's cool about the structure, the spiral double helix structure of DNA, is a result of hydrogen bonding. So if you need a refresher, remember we have two strands of what is it, AGTC, I think. You have a lot of strands of amino acid sequences, and the reason they kind of form this double two-strip helical structure is because there's hydrogen bonding between all of the molecules on both strands. So on the left side you can kind of see the molecules in the strand, and all of those dashed lines in between the two strands are held together by hydrogen bonds. And while they are strong enough to kind of combine the two strands, they're not as strong as the bonds in the molecule themselves. So kind of the cartoon image on the right is, you learn in biology, it's kind of like a zipper. You're able to split apart the two strands, and that's where we pass on our genetics from one side of the parent and to another. They keep kind of splicing and sharing the two strands of genetic code. And last but not least, our third intermolecular forces is called van der Waal or London dispersion. Again, those are just the two names of the scientists. These occur between non-polar molecules such as O2, Cl2, or CH4. When I draw this on the paint, you'll notice that these are very symmetrical, meaning there's no positive or negative side. Okay, so again, notice this picture. The force that's holding the Cl2 molecules together are the ones in between, between the molecules themselves, but not in. So the dotted dashed lines are the things we are focusing on. So what are we talking about? Symmetrical. Again, this was in that article on kind of food and receptors and smell, but one of the questions was CH4, and it showed how the molecule looked like. And we can do the Lewis structure again here. So here's 4, this is 1 and 4, so this is 8. So let me draw my skeleton. And I already have 2, 4, 6, 8. I'm already done with my molecule. And this is my CH4 molecule in 2D. And then we learned we can actually draw this more in 3D. Kind of looks tetrahedral. So it kind of looks like a tripod and then a hydrogen atom on top. Okay. So unlike the HCl molecule, where this is positive and this is negative, the Cl is actually somewhat negative and these are somewhat positive. But you'll notice all of these these directions, they kind of cancel each other out. I don't know if that's easy to see, but because they're all kind of symmetrical in a sphere, these all cancel out. I know that's a little messy, so let's just redraw this here. So this does not act like a magnet. There's no positive and negative section of this molecule. So that's what we mean by not polar. So let's kind of see this more in detail. So what's actually going on in a molecule? Electrons move really fast in a molecule. So on the left side, I'd like you to try to just take it in, try to see the big picture. So those little spheres inside is an atom. So let's say this is Cl2. So you see the two red atoms, Cl2, and they just happen to have two molecules of Cl2. And that little bubble you see outside is actually the region of space that electrons kind of move. If you remember, we talked about Bohr model and just atomic models in general. Electrons fill a space. So that little kind of looks like flubber. That space around is where electrons move. And for the most part, electrons, again, are free to move anywhere, but they naturally are usually even, so the molecule looks symmetrical. But you can imagine in any given time, a very short and small probability is that sometimes maybe all of the electrons start hanging out on the left side of the molecule. So notice for a very brief moment in time, the electrons are uneven. And in this case, it looks like most of the electrons are on the left side of each molecule, making them negative. So hopefully you can see on the right side, it starts looking like a mini version of the dipole-dipole force. So the key message here is for a brief moment of time, a non-polar molecule looks polar. So one side of the molecule looks negative, and one side of the molecule looks positive. And again, like magnets, that's kind of the traction that starts holding them together. Okay, so you'll notice when we compare dipole-dipole versus London dispersion, the dipoles always look like magnets. And these ones, they are sometimes looking like magnets. So if someone can kind of summarize this by answering my question, which forces of attraction do you think are stronger? The ones in the dipole-dipole ones or the ones in the van der Waal? Which ones are stronger?
The dipole-dipole?
The
Because-
dipole-dipole. Why? Or I guess you were about to say something.
I was going to say it's because it has positive and negative charge that attracts, while the the London dispersion is neutral atom or neutral molecules.
It's neutral, right? And when it does look like a magnet, it's only for a very small amount of time. So actually, a lot of these molecules we mentioned, like O2, Cl2, CH4, O2 is oxygen, Cl is chlorine, CH4 is methane. You'll notice what state of matter is this, solid, liquid, or gas? I think you know methane, and I think you know oxygen. Solid, liquid, or gas?
Gas.
They're all gases, right? So where the atoms are actually so spread apart, they tend to not want to be attracted to each other. It's still there, but it's not as much as like the strong liquid or even strongest solids. Cool. So that's pretty much, we'll start looking into the more fun stuff. So intermolecular forces, I want you to start seeing some applications. So one of the things I want to talk about is engineering nature-inspired adhesives. So adhesives, right? Think about glue. It's things that stick together, and engineers and scientists have utilized these intermolecular forces to try to create adhesives. So on the top left, we have a gecko. They naturally have molecules in their feet. So you can kind of see a really close zoom in on the top right. They're essentially adhesives, and even the story of Spider-Man, even though Fiction is somewhat based on some sort of science. Again, adhesives on his palms and legs. So some applications of this is surface tension. We have two examples: the Jesus Christ lizard. I'll mention why that is that, and then water striders. So for those of you who've heard of Bible stories or just Jesus in general, there's always his miracle of walking on water. So there is actually a lizard nicknamed Jesus Christ lizard because it moves so fast and is so light that it can seemingly walk and run on water. And the surface tension is kind of focusing on the strength of attraction of the water. So we actually have this video, so hopefully we can see this.
Some young Costa Rican basilisk lizards are looking
Let me put the volume higher.
for food. Some young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the...
Wait, sorry, can you hear the sound or no?
The audio is cutting in and out a little bit.
Okay, can't know how to do it. Wait, one sec. Alright, let's try again.
Some young Costa Rican basilisk lizards are looking for food. Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, really run on water. It bicycles its hind legs, and the tail becomes a counterweight. We can't know what the snake is thinking. Did it really want to eat the lizard, or did it just want to show?
Looks a bit like a fish, but it's got...
Whoa, okay. Alright, so again, so this is showing the strength of intermolecular forces, in particularly the water. So the water molecules are held together by hydrogen bonds, and we call that surface tension. I'm sure you've encountered that. So it's actually stronger than the weight of the lizard, and it's able to kind of skitter and run across. Water striders again are insects, and they kind of they glide on ponds and just the surface of rivers. So surface tension is just our typical common phrase as a type of intermolecular force, showcasing again the strength of water. You may have heard this also in middle school: cohesion and adhesion. Co means like the same, right? Adhesion is this similar, but when the surfaces are different. So capillary action, every time you've used a straw, is intermolecular forces. Why is your water or liquid attracted to the same liquid to each other? That's cohesion. Adhesion then is why is your liquid, the one that you're drinking, attracted to the molecules in the straw? That's adhesion. So when you apply a different type of pressure as you kind of pull the liquid through your straw, that's capillary action. These are examples of intermolecular forces. The image on the right side, I don't know if some of you have done this experiment, but I know some of my students have done it before. You can do this with sunflowers. Maybe if you're at home and you have sunflowers in your garden, pick one out, and I would persuade you to try putting it into a different dye or dyed water with food coloring, and a capillary action will actually take the dye of your food coloring and it will change the color of your sunflower, again through capillary action. And then as mentioned before, it's used a lot for adhesives. So I want you to see this video again on the quote-unquote the real Spider-Man. So there is a research group trying to invent and learn about different adhesives that can kind of proof of concept of using intermolecular forces in that tape in that video. And then also I do this demo every year, so I couldn't do it live, but I actually did it at 12:30, so I'll show you this video too. Hi everyone, we've been learning about intermolecular forces, and I just wanted to show you a quick demo about how strong they are, and in particular, hydrogen bonding in water. So, in this bowl here is water. You need to just trust me that it is water, and I have a mason jar. And to show that it's open, I'm going to pour some water in here. Hopefully as I do this, some of you may have seen this demo already in middle school, but what I will be doing is taking just a dry card, inverting the bottle, and then I'm going to let go. This is actually something we've learned earlier, and it's just all about air pressure. We have a lot of air outside, and we have a lot of air inside, and you can notice the air outside is much more than the air inside. So the pressure of the air trying to push into it is much stronger than the small air pushing downwards along with the weight of the water. So this is a pretty cool demo with the air pressure outside being much stronger. What you may not have seen though, even if you have it, is this part where I remove the card, and you'll see that the water is still suspended, okay? If you are very keen and you're observing, you'll actually notice that I did cheat a little bit, but there is a little piece of mesh cloth over it, but you'll notice there's still holes in it. But the strength of the hydrogen bonding in the water molecules actually make it much stronger than the weight of gravity. So your next question is, what if you remove the cloth? Well, that hole is way too big, and then that wouldn't work, okay? Other than that, that is my demo, so stay safe, keep on living. Yeah, so that's a demo I did, kind of showing the strength of water, another scenario. Okay, another application, and this will be kind of your assignment for this section. It's on paintballing, and specifically we're going to learn about intermolecular forces regarding solubility, and I'll leave that for you to read. Other than that, this is done. Whoops. I'll put the video here. I have another link for as a resource. This is from Professor Dave. And then more practice on Google Classroom. And then I'd like you to read the paintball article and answer the questions. So again, if we go to our Google Classroom page, it should be under Classroom, Unit 10, Intermolecular Forces. So here's the article. I'd like you to read it. It's only 2 pages. And then answer these questions. Only 5 questions, but I think as you read this, you're going to learn some interesting things about paintballs, interesting things about gelatin, and maybe I will be you can blame me for this, but if you read this, you might not ever eat Jell-O ever again. So that's my disclaimer, but you need to read and find out for why I said that. Other than that, that's it for today. I'm glad a lot of you were able to stop by. Yeah, if you have any other questions or just want to share anything, let me know.